Okay, good morning. How's everyone doing? All ready for the weekend? Long weekend? Ready to get the party started? How about a quiz? Take-home quiz. Since Monday is gonna be off. It's fine. I'm just kidding. My target goal for every quarter is about 7 quizzes at a minimum. 7 quizzes takes us over the threshold of being equivalent to about 2 midterms in terms of time, in terms of the topics being assessed. Okay, so we are still on track to get 7, and so there will not be any quiz next week. So you can relax and enjoy your weekend, catch up on your sleep, catch up on your work, which is what I plan to do. So no quiz. The only assignment is the homework that's due, and the homework will be due on Monday. It's not long. I mean, there are several questions in there. It seems as if it's long, but it's not. Many of those are just short answer questions. And so it's based on the concepts that we already covered in class. And there are like 1 or 2 problems in there. And those problems are what I'll cover today in today's class. So today's class might feel a little rushed just because we are going to cover the concepts, theoretical concept of the capacitor, and then the voltage and current equations, and then we'll look at 2 examples. All right. So it will actually, when I said it feels rushed, but it'll go fast because the equations are exactly the same. There's no difference with the equations. Let me bring up the slides, and then you can talk about. So we saw the equations for a inductor, and the equations for a capacitor are very similar. Okay, they're very similar. So for an inductor, we always talk in terms of the input quantity as being current, right? Current is an input for the inductor, and then voltage is the output. So voltage V for an inductor is L di over dt. Similarly, if we are talking about a capacitor, the equation is exactly the same, except the quantities are flipped. We talk in terms of the input voltage for a capacitor, and the capacitor current I is now C dV over dt. This is a short derivation of where it comes from. We know capacitor comes from the capacity to store energy or store charge. And we determine Q is equal to CV for each capacitance. If we take the derivative dq over dt, dq over dt is nothing but the rate of flow of charge with respect to time. Rate of flow of charge, dq over dt, which is nothing but current. And that's where that equation comes from. Okay, so capacitor current I is C dV over dt. Inductor voltage V was L di over dt. Exactly the same equations. Well, the form is exactly the same. The quantities are switched. So far, so good. Now, a word about the notations. In the inductor equations, I did not have T, which is function of time. That's all it notes. But the equations are still exactly the same. Different textbooks, different instructors, different journal articles will use different notations so that I could be referred to as just I if it's a simple circuit, or it could refer to as IC or IL. Similarly, voltage could be referred as V or VC or VL. If it's a function of time, you could see something like I of t or IC of t, or you could see VL of t. They all mean the same. Whether it is explicitly stated or not, you should understand it's a function of time. Okay, so t is the variable. We would describe equations for the voltage and current in terms of the variable t. Okay, so whether the notation is there or not, it still means the exact same thing, function of time. All right, let's see. Oh, and one final point. So notations, again, are something that you just, it's for the convenience. So if you have more than one capacitor or more than one inductor in a circuit, you might have, I don't know, IC2 of T or VL3 of T. Simply means we are referring to the voltage for inductor number 3. That's all it means. Okay, so capacitor current, Q is from Q is equal to CV. We get I is C dV over dt. Similar to an inductor, obviously, if you take the derivative of a constant, it goes to 0 mathematically. But physically, we looked at the operation of the capacitor, where you apply a voltage, charge starts accumulating. At some point, it reaches the constant value, and then charge stops flowing, means current stops flowing. Current goes to 0. I goes to 0. So what it means is, if you apply a DC voltage to a capacitor, DC meaning it has a constant value with respect to time, at some point, the capacitor will reach full charge. If you apply 5 volts, capacitor will reach 5 volts. And then at that point, current stops flowing. So we say the capacitor acts or behaves like an open circuit. Okay, there is no more charge flowing through. There's no more charge accumulating. And so current goes to 0. Capacitor acts as an open circuit. The value of that voltage or current is constant. It is steady with respect to time. And so this state of operation is known as steady state. So for a capacitor and an inductor, if you apply a DC voltage or current, the response of that capacitor or inductor will eventually reach a state of steadiness, and that state is known as steady state. So for a DC voltage, steady state means an inductor behaves like a short circuit and a capacitor behaves like an open circuit. If you have taken the lab, that is the last procedure in lab number 5, steady state analysis. Okay, steady state analysis. Also, when you apply a DC, well, whether you apply a DC or an AC, the capacitor or inductor, and this is at the beginning of the chapter where I talked about this, it's receiving the energy or it is giving the energy back. When the energy is being transferred, the voltage and the current have different values at any given point in time. So even for a DC applied voltage or a DC applied current, the capacitor or inductor will follow the path. It'll be like an exponential path, okay, where the voltage or current is actually changing with respect to time. Those equations during the charging and discharging phase, we will look at in chapter 4. Okay, we'll look at those in chapter 4. The equations, the general equations for capacitor and inductor are exactly the same. So capacitor current I is C dV over dt. If you wish to find the voltage, all you would do is integrate both sides. Right? You integrate both sides. C is a constant value of the capacitor. You take it on the other side, 1 over C. And then it simply means capacitor voltage is the integral of the current. Quantities are flipped, right? For an inductor, inductor current was the integral of the voltage. For a capacitor, the current, the voltage is the integral of the current. Mathematically speaking, if you are able to solve for one quantity, you should be able to solve for the other one. One side is differentiation, the other side is integration. Two sides of the same coin. Make sense to everyone? Right? Okay. And then, of course, we go through the steps of the integration. We're summing everything up, right? We're summing up the value of the current over a certain time period. So we take the initial time period also into account, which is given by the value of the voltage at time t equal to 0, meaning the time at which you begin your analysis. Okay. Equations for power and energy are exactly the same. electrical power is V times I, the product of the voltage and current. And so you simply plug in the value for the capacitor current in there, and you get CV dV over dt. Okay. Product is, sorry, power is product of voltage and current. Current is C dV over dt. Simply plug in those equation and you get CV dV over dt. That's the equation. Integrate the power and you find the energy, right? And you get half CV squared. It is the total energy stored in the capacitor. Okay, total energy stored in the capacitor. For an inductor, it was half Li squared. For a capacitor, it is half CV squared. It is the total energy that is stored in that capacitor. All right, 10-second pause. Let me know if you have any questions. Does that make sense so far? Yes.
So if a capacitor is like fully charged in steady state, does that mean it has no power?
Sorry, what?
If a capacitor is in steady state, does that mean it doesn't have power flowing through it?
If it's steady state, then yes, that's what it means. So power will also be a function of time, hence P of T, or the potential power at that point in time. All right, so yes.
I was gonna ask, how does the V little one?
Where?
Where that?
Oh, there's a derivation. I mean, we just go in and, finish the calculation and you plug in the limits of the integral and, this is what you obtain. So if, and I sent a message yesterday. I mean, I posted an announcement that I have 3 copies of the book in my office. The students are free, they're welcome to check it out, from my office anytime they want. So to answer your question, the derivation is there in the book. If you wish, you can stop by the office and take a look at it. All right, so there are 4 examples in here, and all of the examples reference the component as a capacitor. Okay, capacitor is 5 microfarads, capacitor is 2 microfarads. Example 3 and 4 also reference a capacitor, but it makes no difference whatsoever. Okay, this example here would work for an inductor just as well. All 4 examples would work for an inductor also. The only difference would be that in examples 1 and 2, it would be flipped. In example 1, we would do a derivation. In example 2, we would do an integration. For an inductor, it would be flipped. Okay, so here you perform a derivation. Here you perform an integration. So for an inductor, it would be integration. And here it would be derivation. No difference. Also, this is simply a mathematical solution. You're given an expression. You're already given an expression for the voltage and the current. All you have to do is apply mathematical calculation and you have your answer. In the interest of saving time, and I wish to actually completely cover examples 3 and 4, I'm not going to do 1 and 2 in class. What I will do is I will either post a video or I will post a slide and I will add it to the class notebook. Okay. Again, it is self-explanatory. You take V of t and you do dV or dV over dt. Form a derivation. It's a simple cosine function. You perform a derivation with respect to time and you will have your answer for I of t. I will post, again, as I said, I will post either a video or I will add a slide to the notebook. Yes.
So for number 1, if that was an inductor, you said you would integrate? And that would give you,
Yes,
okay,
yes.
so
Yep. It's simply flipped, right? For an inductor, if I of t is given, you simply do L di over dt or di over dt, perform a derivation, multiply with the inductance, and you have your inductor voltage. So if you want to find the inductor current, then you perform an integration. So again, all solved examples apply equally to capacitors and inductors, except the approach would be flipped. What I'm more interested in covering right now in this class in person is piecewise linear analysis. How many of you have used this technique or come across this technique in your own fields? Yes, at least one of you. So you also, so at least 2 or 3 students. All right, so piecewise linear analysis, it's similar as a concept, it's similar to superposition. You take a large, portion and you divide it into small pieces, okay? The advantage here is that in the previous 2 examples, examples 1 and 2, we already had a mathematical expression given to us. Here it's a graphical interpretation of a signal that is being applied, okay? So it's a capacitor of 5 microfarads, and you're applying a voltage that is described graphically. This graph cannot be expressed directly in any mathematical terms, okay? But if you look at it, we can see that if it is broken up into smaller pieces, each piece has a linear relationship with time. Okay, and in this case, the piece is here between 0 and 6. Okay, I will call this time period T1 and time period T2. And within each time period, the voltage as a function of time has a linear relationship with time. It is varying, it is not constant, but it is linear. And because it is linear, it is a straight line which has a slope. I can use the slope line intercept method to write an equation for that line and describe the voltage as a function of time. And once I have that mathematical function, I can apply my equations and I can find the voltage and current, as the case may be. Even more importantly, the beauty of this method is that you have time on the x-axis, right? And we're using the slope line intercept method. You have time on the x-axis and your voltage on the y-axis. If you describe the slope of the line, it directly gives you dV over dt, rate of change of voltage with respect to time, or simply the rate of change of voltage, dV over dt, which is what we want in our equation, dV over dt. And that's it. So it's rather straightforward. So just as a refresher, actually, let me describe T1 time period refers to T value between 0 and 6 milliseconds. Attention to detail. Okay, extract as much information as you can from the given problem. In this case, it is not explicitly stated, but a small error of overlooking the units and the unit prefix will mean that your answer will turn out to be incorrect. So here the units on the x-axis are labeled as milliseconds. And so you have to take into account 10 raised to minus 3. All right, so time period T1 is between 0 and 6 milliseconds. Slope, a line is described by this equation. Y is equal to mx plus b. M is the slope, b is the y-intercept. There are different forms and different notations used throughout the world. This is the notation that we use, or I used. I've also seen C instead of B. This is the y-intercept, and x and y, of course, x is time, and then y is v in this case. And slope can be given by any two coordinates or any 2 points on that line. So M1, I can write as 24 minus 0 divided by 6 minus 0 milliseconds. So it'd be 12 volts per millisecond, or 12,000 volts for every second. No, sorry, not 12, 4. 4 volts per millisecond. And then I already established that dV over dt is equal to M. So I, capacitor current I, is simply given by C times M1. I'll label that as I1 for the first time period. I1 or IT1 doesn't really matter, notation. The point is the capacitor current in the first time period is given by the expression C times M1, C dV over dt. So simply multiply the capacitor value with the slope of the line, you get an answer, it's 20 milliamps. And that's it. That is all the calculation that is required. Easy enough? Let me know if you have any questions. Make sense? Right? In the second time period, if I go to T2, it is between 6 and 8 milliseconds. Okay. And so M2 would be 0 minus 24 and 8 minus 6 into 10 raised to minus 3. So now I have 12, minus 12 actually. Okay, minus 12. So minus 12 volts for every millisecond. Multiplied with 5 microfarads capacitor, you obtain 60. Right? Minus 12 into 5, minus 60. And when you plot it for that first time period, you have plus 20. And then here, you have minus 60. And that's it. That's how we find a capacitor current if you're given the voltage. Simple derivation. The mathematical calculation is separate, but the problem setup, basically we apply piecewise linear analysis where we describe each piece using the equation of a line. In this case, we simply have to write the slope. Once we're at the slope, that's it. All right, any questions? Does it make sense? Right? The reason why we split it up and the application and how to apply the concept. All good? Okay. Then let's look at an example where you're given the current and you're asked to find the voltage. So now it's the flip side. So now we'd have to integrate. Okay, now we'd have to integrate. Quick point. If this was for an inductor, instead of performing a integration, we would perform a derivation, right? So here we would find the slope of the line for the inductor and simply find di over dt. In the previous example, in this previous example for an inductor, you would integrate the voltage to find the current. So IL would be given by integral of VL. So you would integrate. Once you have the equations for I of t, you would perform an integration and then you would find the current. And here is the exact opposite. And that's why I said all four examples work equally for both capacitors and inductors. Okay. All right. So here I can see again, it's a 4 microfarad capacitor. I can see that I can break up that input signal into individual pieces, and each piece can be described as a linear line. So in this case, time period T1 and time period T2. The max value is not easily visible, but it is 16 microamps. 16 microamps. And this is -8. So 2 time periods. The first one goes from 0 to 2. The second one goes from 2 to 4. Let's take a look at time period 2. And the reason is it's a flat line. It's not a function of time. It does not change its value with respect to time. It's a constant. So I can simply write it is 8 microamps. Okay, I can simply write 8 microamps. Constant, does not change with respect to time. So for T2, I is -8 microamps. That's it. DC value. So it's a DC value. I know eventually it should go to 0. Or actually, the current is constant. Sorry, not 0. Yes.
Why does the number down there say -6?
Here,
No, 16 times 10 to the -6 over 2 times 10 to the
mm-hmm. Because it's micro. Yeah. But good point. Good point. So T2 is straightforward. Let's tackle T1 and describe the function for our current. So in T1, we go from 0 to 2 milliseconds. And I can write the slope. Slope would simply be 16 times 10 to -6. Actually, 16 minus 0 times 10 raised to -6, because it is 16 microamps. And this will be 2 minus 0 times milliseconds. The slope is 8. And y is equal to mx plus b gives me equation I, 8 times 10 raised to -3 times t. And b is, of course, 0. This equation describes the value of the current only between 0 and 2 milliseconds. So be very clear about that, okay? This is still the initial setup. We are still setting up our problem. This is the equation that describes the value of the current between 0 and 2. And then we perform our integration. Okay. And here's important points to note. For T1, our time period is 0 to 2 milliseconds. Our input current is a function of time. So our output voltage, or the voltage that we're calculating, is also a function of time. So the equation that we obtain should be a function of time. So our integral, when we perform our integration, we have limits. And limits will be the start point of our analysis, T0. Okay, T0. The start point of my analysis is T0. And for this particular piece, the T0 is 0. Remember, T0 does not mean time equal to 0. It simply means the point in time at which you begin your analysis. For this piece, we begin our analysis at 0 milliseconds. So T0 is 0. And then the other end of the limit of the integration is a function of time. So it's the variable time, variable t. Okay, so it goes from T0 to t. And that's the limit of the integration of the integral, which is right there, 0 to t. V, voltage at time t equal to 0, meaning the initial stored energy in that capacitor. And in a problem statement, if it is not explicitly stated, you can assume it to be 0. Okay, you can assume it to be 0. So V0 here is 0 volts. There is no initial stored energy at time t equal to 0. Otherwise, the problem statement would itself state, at the beginning of the analysis, capacitor 4 microfarads was charged like 5 volts. And then you would have to take that into account. If it's not stated, then it's 0. So the only thing we do is plug in the values for the capacitor and for our current, and you perform the integration. So 1 over C is right here, 1 over 4 microfarads, and then our integral, 8 into 10 raised to minus 3. The time t changed to x. Simply because the limit of the integral is also t, then to avoid any confusion, we simply change the value for that function as x. You can change it to anything you want, a, b, c, d, e, f, g, x, y, z, doesn't really matter. Okay. Because if you use t in there, it just causes confusion. So you change it to x. So when we solve this, we simply get what? V of t is 8 into 10 raised to minus 3 is a constant, comes outside. This is 4 into 10 raised to minus 6. So x dx gives me x squared over 2. Take the 2 outside. 8, 4, and 2 cancel out. I'm simply left with 10 cube. And then you plug in limits of the integral, which is 0 and t. You end up with t squared. And that's the answer, 10 cube t squared. So voltage can be described by the expression 10 cube t squared between 0 and 2 milliseconds. Is everyone clear on that? Again, the math is not something new, right? The math is straightforward. Even for a differentiation or integration, it's straightforward. There's nothing complicated about this. And as engineering students, I would assume that you're probably more familiar than I am because you've just taken those classes. Right? The more important point is that you should understand how to apply each and every point of that equation, or each and every quantity of that equation. So everybody understands T0, right?
Yep.
Everybody understands the variable T and why we take it. So then we move to the second time period. And here, in the second time period, our start point is 2. Start point is 2 to 4 milliseconds. So here in this piece, my 2T0, my starting point, the point at which I begin my analysis, is 2 milliseconds. So T0 is 2. And then voltage at time t equals 0 is the voltage at time 2 milliseconds. And the voltage at time 2 milliseconds was given by the expression in the first time period. So I plug in t equals 2 milliseconds in my equation, and I obtain a value of 4 millivolts. 4 millivolts. So when I begin the analysis for the second portion right here, the capacitor already has a stored energy, and the amount of the stored energy is given in terms of voltage as 4 millivolts. And I have to take that into account. Otherwise, my answer would be incorrect. So this is voltage, or the initial stored energy present in that capacitor. So again, just because it says T0 does not mean T equals 0. It means simply the point in time at which I began my analysis. And once I account for that, it simply means I add it up. And then I plug in the values, minus 8 microamps. So V of T would simply be minus 8 microamps. I'm going to take this outside. 4 into 10 raised to 6, or 10 raised to minus 6. And then note this. The limit of the integral is 2 milliseconds, 0.002. Again, attention to detail, 0.002. And upper limit is t. And then, of course, this is simply dx. So we solve this and we obtain minus 2t plus 8 into 10 raised to minus 3 volts. There are a couple of steps involved in there, of course, but those are rather straightforward and simple. Integral of dx would simply give you x. You plug in the values of the integral, t and 0.002. Then add it to the minus 2 that's outside. And you should obtain minus 2t plus 8 into 10 raised to minus 3. Make sense? Right? All right, any questions? Again, the important concepts you have to take from here is the limits of the integral and the initial starting point of your analysis, T0. And the problem in the homework is very similar to this. You're asked to find the voltage of the values, the values of the voltage, current, power, energy, and simply plot it. Once you have your equations, you can plot it. Right? I have my equations. The first one is 10 cubed times t squared. And the second one is, of course, linear, minus 2t. Right? So that gives you an idea of what kind of waveform you should expect. If it's simply t, you know it should be a straight line with a slope. Right? So in the olden days, in my day, I would like to say in my day, long time ago, you would simply do a manual calculation. So each one of these equations, and depending on how many data points I want, I will plug in manually in the calculator, calculate it for t equal to 0.1, t equal to 0.2, 0.3, so on and so forth. Now you have programmable calculators, you have software, Excel, MATLAB, MinTab. There are so many other software out there that can do mathematical calculations. Simply plug in the equation, plug in your values, and it spits out an answer in like a second. Okay. Whatever method you choose, as engineers, you should be able to take these values and create a waveform out of that, plot a chart. And so when you plot the chart, it looks like this. All right. So does the entire problem or the solution make sense for both the voltage and for the current, right? If it's a capacitor, we perform a derivation integration. If it's an inductor, we perform an integration and derivation. But the examples apply equally to both. There is no difference whatsoever. Any questions at all? Anyone? Okay. Then let's look at what happens if you connect capacitors in parallel and series or inductors in series and parallel. Similar to resistors, where we reduce a large network of resistors down to one single one, we can find LEQ for a series network as simply L1 plus L2. If you have a parallel connection, LEQ is simply, again, the sum of the reciprocals capacitors in parallel also add up the exact same way. So C1 plus C2. And capacitors in series add up the opposite way. So we have 1 over C1 plus 1 over C2. Okay. So inductors add up the exact same way as resistors. Capacitors add up the opposite way. Capacitors in series is 1 over C1 plus 1 over C2. Capacitors in parallel is simply C1 plus C2. We won't, in 201, I do not usually test anything where I would take a large linear network of capacitors and inductors and ask you to solve, for the voltage and current that way. But you should be aware of if you have like 2 or more capacitors in parallel or 2 or more resistors, 2 or more inductors in series or parallel, you should know how to reduce them down to one single component. Right. On the last slide, I simply have a summary of all the equations that we applied in this chapter. You see series and parallel equations are right here at the bottom. And then all the voltage, current equations, power, energy, everything's there. You can have all equations on an equation sheet for the quiz and the final exam. As long as you know how to use them and apply them, that's all I care about. They're all tools in your toolbox, but you should know how to use each and every tool. Okay. All right, so that's the end of chapter 3. Homework, as I said, is not, you see a lot of questions in there, but it's not long. There are about 8 or 10 questions, but most of them are conceptual short answer questions. And then there are 2 or 3 problems in there. And the problems are, I think there's piecewise linear analysis. Several students also have started, and some of them have already completed the homework. Just because, if you've done piecewise linear analysis previously, then it's rather straightforward. Okay. All right. Any questions? Any questions at all? Eager to get the weekend started? Everyone? Yeah. Before you leave, a student actually had asked me, if you remember last week, they asked me about music and songs. So I thought I'd share this. Let's see. This was a Norwegian dance group. They call themselves Quick Style. And so it's two brothers, and they actually won Norway Got Talent, the version of America Got Talent. And so they won this in like 2009 or something. They've actually choreographed dance sequences for BTS. I didn't know that. And this was at one of the brothers' wedding. So the songs that they dance to are they're from like Indian movies. I'm from India, if you didn't know that. So let me see. I muted this. I'm gonna unmute. So let's see. So this was at one of the brothers' wedding, and they did this. Anyway, I'll leave that. The original song that they are playing in the background. This actually an entire compilation. But what happened was when they posted this online, this was a few years ago, I think 2 or 3 years ago. It quickly went viral within like a month or so, and all around the world, people were actually creating short videos of the exact same choreographed steps, and they were posting online on YouTube videos, YouTube Shorts, or TikTok, and people all from like South America, US, Europe, Africa, Asia, everywhere was using this music to do it. Anyway, I just thought I'd share this. The original song is known as Kala Chashma. Kala means black, Chashma is glasses. It literally just translates into sunglasses. And so the line of the song is basically, you look really good in sunglasses. And that's what it is. But that's the original song. I'm not going to play that. You can look that up and play it over the weekend just to get your party started. Anyway, I'll bid you all a good weekend. Have fun, enjoy, get caught up on work, get caught up on sleep, and I will see you all on Wednesday. The only assignment is the homework assignment. All right. See you all next week.
Actually got